So,
Okay.
yeah, so good evening or good morning, everyone. On behalf of the IIChE Student Chapter slide and the Department of Chemical Engineering slide, I welcome you all to the fourth talk of the IIChE lecture series. Today, we are delighted to have Professor Aydil with us. Before I move further, let me give you a brief introduction about him. So, Professor Aydil is the Alstad Lord Mark Professor of Chemical and Biomolecular Engineering at New York University, Tandon School of Engineering. Previously, he was the Ronald L. and Janet A. Christensen Chair in Renewable Energy and Executive Officer of the Department of Chemical Engineering and Material Science at the University of Minnesota. He is also a fellow of the American Vacuum Society and editor-in-chief of the Journal of Vacuum Science and Technology. Regarding his education, he received his PhD degrees in chemical engineering and in material science and engineering, both from UC Berkeley in 1986, and he received his PhD in chemical engineering in 1991 from the University of Houston. He has published over 200 articles and holds 7 patents. In recognition of his research, he has received the Peter Mark Award and the Plasma Prize from the American Vacuum Society and many other notable awards. And at the Tandon School of Engineering, Professor Aydil's group conducts research in electronic, optoelectronic, magnetic, and catalytic material synthesis and characterization with an emphasis on understanding synthesis, structure, property, performance relations. So today he will be introducing us to one of his recent works, jointly with Dr. Tran and Dr. Cleveland, titled Quantum Cutting and Rare Earth Doped Halide Perovskites. Before we begin, just a couple of quick points. It would be great if everyone could turn on their videos so that we reach closer to an in-person talk, something which we have been missing out for quite a long time. And also, if you have any questions, you can put them in the chat or you can directly ask Professor. And if you put them in the chat, then the moderator should convey them to Professor Aydil at the appropriate time. So without further delay, I invite Professor Aydil to deliver the talk. I hope all of you will enjoy the same. Over.
I hope you can hear me and see my slides.
Yep.
Great. So first of all, I want to thank you all for inviting me to give this talk and for being here. I want to say that I have a hard stop at 10 o'clock. I will have to leave. However, if you want to talk more about anything that I'm going to talk about, you can just email me and we can have a separate conversation with a group of you or one-on-one. I am going to talk about the most recent work that we're doing on increasing the silicon solar cell efficiencies above fundamental limits using something called quantum cutting. And the work is done by my graduate students, Min Tran and Ivor Cleveland. And I want to say you can follow me on Twitter and you can also join my network at LinkedIn. So I have quite a bit of a group of network of scientists, and I post things that has to do with science, Journal of Vacuum Science and Technology, etc. So without further ado, I'm going to start my talk. First, I want to tell you a little bit about NYU. So I don't know how much you know about New York, but the central part of New York is in Manhattan Island. Surrounded by the Hudson River and the East River. And NYU, the main campus, is centered around Washington Square, but it's actually all over the place in New York. So it's a very distributed campus. In fact, the engineering is right across the river on this side here in Brooklyn. So you have to pass a bridge or go under the river in a subway to get to Brooklyn from the main campus. Or you can walk across the Manhattan Bridge, which I do when the weather is nice to come to work. I live on Manhattan, and then I walk across the East River to get to work. And this is Tandon School of Engineering. We have 2 main buildings and some floors of surrounding buildings. It's a urban campus It's open. It's in the city of Brooklyn, right in the downtown of Brooklyn. And this is the entrance to our building. And when I go home, if the timing is right, I can get a view of the sunset. And these are pictures. These are pictures that I actually took as I was walking home one day. So that's all about NYU and Tandon School of Engineering. Let me tell you about what we're trying to do. And all my students nearly are working on some aspects of this problem. And I picked one material today that I'll tell you about. It's not necessarily the best performing material. Unfortunately, I can't talk about the best performing material just yet. But I think it'll give you a flavor of what we're trying to do. So here's the problem. Silicon solar cells dominate the market. That's a good thing. However, silicon solar cell efficiency has stalled. It has only 2%. Okay, so this shows the silicon solar cell efficiency, and from 2000 to 2020, it has only increased by 26.7%. So all the penetration of silicon solar cells into the market and increase is due to changes in the cost, or the decrease in the cost of making the silicon solar cells. It would be nice if we can increase the efficiency further so that we can decrease the cost of electricity production per kilowatt hour, okay? Now, the reason for this is that we're approaching something called the Shockley-Quessier limit. That is a fundamental limit set by nature on all solar cells that are based on a single material with a bandgap. So for this audience, I'm going to describe the nature of that Shockley-Quessier limit. It arises from the physics of how a silicon solar cell or how a solar cell works. So the way that solar cells convert sunlight to electricity is by creating electron-photon pairs in the conduction and valence bands, respectively. So if the light comes in with energies less than the band gap, the distance between the conduction band and the valence band, it cannot excite electrons into the conduction band, so that light is useless. It has to come in with energies at the band gap or larger to be able to create electron-hole pairs, and those electron-hole pairs then are extracted to get the current out and have the solar cell working. If, on the other hand, you have light that has energy larger than the band gap, you create excited electrons and holes deep up in the conduction band or in the valence band. Now, those excited electrons quickly relax to the band edges by colliding with the lattice atoms and by making them vibrate, in other words, creating heat. And that energy is lost as heat. You don't get it as potential voltage or as current. So that's energy lost heat. So if the band gap is too small, then you lose a lot of energy by heat. So if the photons come in with energies less than the band gap, then they can't excite any electron-hole pairs. They have to come in with energies at least the band gap, so that you create electrons and holes, which are then turned into current and extracted from the solar cell. If they come in with energies higher than the band gap, then these electrons quickly relax to the band edges by colliding with the lattice atoms and making them vibrate more, and therefore creating heat. And that energy is then lost as heat. You don't recover it as potential or as current. So for a given semiconductor that you're going to make a solar cell out of, if the band gap is too large, then you throw away a lot of the photons. If the band gap is too small, then you lose a lot of the energy as heat. So there is a happy medium, and calculation was done back in 1961 by Shockley and Quessier, and they showed that there is a maximum And so these are all the solar cells that have too high of a band gap. These are all the ones that have too low of a band gap. And it turns out that the silicon is roughly at the maximum, but there is a maximum efficiency right around 33%. And practically we're at about 25% now, so we're getting close to that limit. There are a whole bunch of reasons why you lose the efficiency and you don't get to the ideal limit, but it would be nice if this curve was higher. So that energy lost, this is a plot of the fraction of the energy lost. So there's a lot of energy lost due to relaxation to the band edges, okay? And the reason is there's a lot of electrons with high energy in the solar cells, in the UV and blue, and the band gap for silicon solar cell is peaking in the near infrared, okay? So one way to surpass the Shockley-Quessier limit is tandem silicon solar cells. What that means is that you take different semiconductors with different band gaps and you stack them together. And different semiconductors absorb different part of the spectrum and convert it to electrons and holes. And that's one way to surpass the Shockley-Quessier limit. However, look at how complicated these structures are. Many, many layers. So it adds to the complexity and it adds to the cost. So you'd like to find another way. So that another way, which I'm going to talk about, is what's called quantum cutting. So this whole problem is arising because the solar spectrum is not well matched to the silicon's band gap, okay? So silicon's band gap is around 1100 nanometers here, whereas as you can see, there's a lot of high energy photons in the solar spectrum. It would be nice if we took these blue photons and make 2 photons of lower energy. This 2 is a typo. It should be 1 band gap. So we take twice the band gap energy out in the blue, and we make 2 photons of 1 band gap energy, which is depicted here with the schematic here. So you'd like to put a magic material on top of a silicon solar cell, and that magic material takes all the blue and UV photons and with 200% efficiency creates near infrared photons, and that's called quantum cutting. So that would basically make the spectrum look something like this. So it decreases the losses due to relaxation to band edges. So you're essentially exciting to the band edges directly, not deep into the bands, okay? So that's one advantage of having a quantum cutting material. But there are also other advantages. So one thing is that quantum cutting also shifts absorption to wavelengths where silicon solar cells are more efficient. So this plot shows 2 things. One is normalized solar spectrum in black, and then also silicon solar cell external quantum efficiency. So this is the efficiency at which a given wavelength of photons are turned into electrons or current. So if you look in the UV, the efficiencies are decreasing rapidly, right? Going from at 500 nanometers, something like 70% down to even less than 20% by the time you get to 300 nanometers. On the other hand, in the near infrared, it's close to 100% or 90%. So this quantum cutting of taking these photons and putting them here also shifts to regions where the solar cells are more efficient. And this has to do with shallow UV absorption near interfaces where recombination or losses of electrons is high. So you get 2 benefits. One is due to better matching and also shifting it to where the silicon solar cell is better. So I won't bother you with the calculations, but if you sit down and calculate and repeat the calculations that was done back in 1960, you come up with the following numbers. So the current record is about 27%. The theoretical limit, as I told you, is about 33%. So if you can do this quantum cutting, you can raise the theoretical limit from 33% to 41%. Okay, not all of that could be recoverable. There are all sorts of inefficiencies. So this shows here the new Shockley-Quessier limit with quantum cutting. This is where we are. So in principle, you could raise it up to here. But if you look at some realistic goals, a realistic commercial goal could be 35%, and that's still above the theoretical limit. Okay, so there's a great benefit of taking a silicon solar cell and putting on top of it a material that quantum cuts, which we call quantum cutter. Okay. Moreover, it's a drop-in, right? So you don't have to change your production of the silicon solar cell. All I'm going to do is do a coating of this, and it's going to increase the efficiency. So this sounds sort of too good to be true, and there is nothing new that I'm telling you about the principle or the idea, except that that magic material did not exist. People looked for it for 60 years, and finally, people discovered a candidate after 60 years of looking by accident. Okay, so in 2017, a group in China, Song et al., accidentally discovers this magic material, and the magic material is cesium lead chloride, a halide perovskite that is doped with ytterbium, and they discovered it in nanocrystals. I'm going to show you that it doesn't have to be nanocrystals, but the ytterbium is important. And so here, what they were doing was essentially taking perovskite, halide perovskites, the hottest material, so there's a lot of paper being written, and they decided to put all the rare earths into the cesium lead chloride and see what happens. And what they discovered was that when they looked at the photoluminescence quantum yield, that is how many infrared photons that you're making per UV or ultraviolet photon, for most of the rare earths, it was about 30% what you would expect. But for ytterbium, they got over 100%, which is a clear sign of quantum cutting, that you're getting on average more than one photon in the near infrared per photon in the UV. Okay. Now, since discovery of this material, people have reached 200% photoluminescence quantum yield with this material, shown here. However, it saturates with increasing light intensity and the quantum yield decreases. This is a bit of a problem because the sun flux is about there. So it's low photoluminescence quantum yield under AM 1.5 conditions. I won't talk about how one can remove that, but one of the reasons is that ytterbium 3+ doping is difficult in colloidal synthesis. You can only put 1 to 8% of ytterbium into the material. Now, what you might say, why does this happen? And the answer is we don't know. Mechanism is not understood. It is a lucky accident. But one hypothesis invokes that there is a ytterbium 3+ induced defect slightly below the conduction band edge, and you have an efficient energy transfer to ytterbium 3+, and you have a charge compensating lead vacancy defect complex that mediates that transfer to the ytterbium. Okay. Another one invokes a blue photon getting absorbed and then getting trapped into a defect, and then that getting coupled into 2 ytterbium 3+, and then near infrared photons being emitted from the ytterbium 3+. Okay, and this energy is very close to the silicon band edge. So ytterbium is like perfectly matched to the, nearly perfectly matched to the silicon band edge. Now, what does that defect look like? People have various hypotheses, but this is the structure of the cesium lead halide perovskite. So here's the cesium atom. Here are the lead atoms in the centers of these octahedra, and these are the halogen atoms that form the octahedra. So if I take out 3 of the lead ions, that's Pb is 2+. If I take out 3 of them, I took out 6+. I put in 2 ytterbium of 3+, then you have 2 ytterbium 3+ in close proximity of a vacancy. And the idea that people are thinking is that this vacancy traps the electron hole pair, the exciton, and then because the ytterbium are in close proximity, then energy from this defect can closely couple to the ytterbium. Whether this is true or not is an open question, but it is the leading hypothesis. Okay. So the question that so I gave you the background. So what I want to tell you is what we're doing. So we're trying to answer the question of, are there other lead-free quantum cutting materials? So beyond the cesium lead chloride, or is it sort of unique? And the reason is that lead, we don't like to use it, right? So we'd like to get rid of lead. And we're working with Cesium Bismuth Perovskites. So bismuth is non-toxic. One thing is that the bismuth 3+ and ytterbium 3+ are isovalent. So one can get around this limitation of putting limited number of ytterbium 3+ into the material, that you're limited to 1 to 8% because lead 2+ and ytterbium 3+ are not isovalent. And if you look at what you can make with cesium and bismuth, there's a host of compounds that you can make of different stoichiometry. And we actually looked at a number of them. I'm going to focus on just a couple here. And if you look at it, the way that you can control it is by changing the ratio to cesium bromide and bismuth bromide, which will be the precursors for making these bismuth perovskites. Okay, so I'm going to focus on two of these. One is cesium 3 bismuth 2 bromine 9, which is a trigonal material, and then the other one is 316 cesium bismuth bromide. And the structure of that is there's a little bit of controversy. We and some others think it's monoclinic. And the only thing that I'm going to point out here is that if you look at these octahedra, in the cesium 3 bismuth bromide, they're not connected, corner connected. They're just sort of distributed and independent. Whereas in this material, they are corner connected. You can't see all the connections here. I'm just showing you here. But if I were to rotate this, you will see all the other connections too. Okay? Now, we do our synthesis using reactive physical vapor deposition via co-evaporation in a glow-boxed chamber. We have 6 sources into which we can put various metal halides. And we have a combinatorial mass that allows us to deposit many, many materials at once. And it's all programmable. So we can go through many different compositions relatively fast. And for the rest of the talk, I'm going to focus on where the sources are: cesium bromide, bismuth bromide, ytterbium bromide. Deposition temperature is 30 degrees centigrade. Typical film thickness at about 500 nanometers, 460. About 2.5 angstrom per second. And we anneal them at around 300 degrees centigrade. Okay, the advantages of this is that we can do combinatorial synthesis. There are no solvents, as opposed to people making it using nanocrystals. We have very good stoichiometric control by using active control of the rates using quartz crystal microbalances, very reproducible and uniform films. And this is my group working on this material. Okay, so the first thing that I'm going to tell you a little bit about is some optical properties of cesium 3 bismuth 2 bromide 9. So it's a little bit of a detour, but it's good to understand the optical properties to appreciate what I'm going to show you. Okay, so when we first got into this material, and you know, all good students go and look at published data. And what we noticed is that the published optical absorption and photoluminescence data varied significantly. It's really all over the place. So here is all different materials made, and this is optical absorption. They are shifted for clarity. But what you can see is these peaks are appearing at different locations. And presumably, this is from all the same material. They're all supposed to be the same. Now, what is important that I want to point out is that all these syntheses have in common that they are solution-based. Basically, you know, somebody comes up with a synthesis technique and many people repeat it. They have slight variations on it. But what they have in common that they use bismuth bromide. They're all in solvents, liquid methods. They all use oleic acid, typically for capping the colloidal particles, and in various solvents, organic solvents. Now, you might say, well, they're making nanocrystals, so this shift might be due to nanocrystal size quantum confinement. And it's not, because there is no clear quantum confinement trend. You would expect smaller nanocrystals to appear blue shifted compared to large nanocrystals. And here I show 2 examples and the trend is reversed. So it's not due to that, okay? Now, I want to point out one interesting fact. Notice that bismuth bromine 6,3- ion. So if you make a liquid solution, you don't even make the material. You just make, you put a salt of bismuth bromide 6 into any solution. It absorbs at 386 nanometers. So there's not even solids at that point, okay? So these bismuth bromide octahedra themselves absorb at 386, okay? And the same thing for photoluminescence. Photoluminescence peak is all over the place. PL peak locations vary from 390 to 476. And the blue shift, again, is not due to quantum confinement. And photoluminescence quantum yield reported varies from 0.2 to 46.4%. People making big deal out of this, that it's almost 50%, and you can make light-emitting diodes and things like that. There's a lot of that stuff in literature. Now, when we make our optical absorption from PVD films, now there are no liquid, no chance of contamination from oleic acid, bismuth bromide 6 ions, etc. Depending on which material we make, if we make the 329, we get a optical absorption peaking at 435. If we make the cesium-3 bismuth bromide, we get an optical absorption at 383, okay? And we assign these transitions to localized transitions on these purple BIBR6 octahedra. Note that the 383 coming from this material where the octahedra is isolated. And even though this is solid, note that if I were to have BIBR6 3- ions in liquid, it would look a lot like this, right? So it looks like a liquid absorption because the octahedra here are not interacting. Here, they're corner-corner sharing, they interact, so there's a shift to 435, okay? So it looks like a liquid solution, and so in fact, if I make the liquid solution and it overlaps with the solid, and I know that it's not contamination. However, if you were to make it with liquid, there could be contamination, and it could shift depending on the solvents, because that Bi3 plus is forming complexes with anions and ligands and solvent molecules, and it can fool you into thinking that that's coming from the solid solution. So we think that the reported absorptions are not from the solids of 3 to 9, but from bismuth complexes, or possibly from if you made the impure CS329 with some CS316 material in it. So, previously reported blue shifted photoluminescence due to quantum confinement, etc., we think are incorrect. Okay. In fact, my student took all the published data that were claimed to be coming from nanocrystals, and she could reproduce the photoluminescence identically just by putting BIBR6 in solvents that the reported work has used, and just by contamination, without even solid, you can get basically the identical photoluminescence. And so we think that a lot of the work is contaminated, okay? And in fact, the 46.4% photoluminescence quantum yield is not from 329, it's coming from these solutions. So to cap now the known trustable absorbance in photoluminescence, absorption peaks at 433 nanometers, absorption onset at 466, consistent with a band gap of 2.66 electron volts, and photoluminescence at 472 nanometers, but it's weak. And so the photoluminescence lifetime is less than 1 nanosecond. So that says that there is a lot of very fast non-radiative recombination in that material. In fact, the highest trustable visible photoluminescence quantum yield is not 50%, but it's less than 1%, about 0.2%. So that's going to become important in a minute. Okay. So I wanted to sort of convince you that within the limitations of X-ray diffraction and Raman spectroscopy, the films that we make using this solid physical vapor deposition technique are phase pure. This is the simulated X-ray diffraction, and this is the thin film. All the peaks match. There is some texturing, and the Raman shows that it is phase pure, and when we compare it with potential impurities, we don't see anything in our thin film. So we're confident that our optical absorption and photoluminescence is correct. Okay, so now getting back to quantum cutting, let's do ytterbium doping and see if there is any conversion into the near infrared. So we increase the amounts of ytterbium bromide added to co-deposition of cesium bromide and bismuth bromide. So we turn on another one of the sources. And I'm going to report percent ytterbium as the ratio of ytterbium to bismuth. So we started with the hypothesis that ytterbium substitute for the bismuth. And we put up to 50%, so about half of the bismuth substituted with ytterbium, or put enough ytterbium in there to substitute half. And you can see that the X-ray diffraction doesn't change very much. It remains trigonal, at least up to 50%. And so our hypothesis is that ytterbium 3+ substitute for bismuth 3+. There is also a shift in the Raman, as you would expect. They broaden and shift as ytterbium 3+ substitute for bismuth 3+. I'm going to go a little bit faster to make up for the time that we lost at the beginning, so that I can get some of the some of the results. And then there's also this sort of as you start putting ytterbium, you start getting these broad peaks, which we think are due to ytterbium bromine vibrations. It's small. But it is there detectable. So we think that the ytterbium 3+ is indeed going into bismuth 3+, and the size of the ion also is such that it can do that. Moreover, it's difficult to explain putting 50% ytterbium and not seeing any other phases appear. It has to go someplace without disturbing the overall structure. Okay, the UV vis absorption, there's not much of a change. It peaks still in the same place, so that is a sign that the corner sharing of this BI-BR6 octahedra network is maintained. There's a little bit of weak absorption at 383 nanometers for films with greater than 30% ytterbium. We think that there might be some of the 316 phase appearing. So the question is now, do these films emit in the near infrared? And the results are very encouraging. So I'm going to show you visible and near infrared emission from ytterbium dope. So first of all, visible emission at 472 nanometer. And recall that, you know, when people made the nanocrystals, the trustable data showed photoluminescence quantum yield is weak, 0.2% at most. And we basically get the same result. It's a very weak photoluminescence in the visible. So that is a sign for fast non-radiative recombination, okay? However, there is surprisingly strong near-infrared emission at 1000 nanometer, where you would expect from the ytterbium 3+ ions, okay? And in fact, we have a highest photoluminescence quantum yield of 14.5% of this is basically the highest for any non-lead containing material. So there's a sweet spot as you put the ytterbium, but it drops off. And remember that I also told you that a small amounts of a new phase might be appearing as the optical absorption shows. So if you can get 14.5% photoluminescence quantum yield in the infrared with little visible emission in presence of non-radiative recombination, which is very fast, that tells you that the near infrared emission is very fast. The transfer into the ytterbium ions is very fast and can compete with non-radiative recombination. So by putting in ytterbium, we introduced a fast near-infrared radiative mechanism with ytterbium doping that competes with that fast non-radiative recombination. And that's very encouraging because you expect quantum cutting to be very fast. So we have a new mechanism coming in. To show that it's exactly quantum cutting, we have to go above 100%, and that's what we're trying to do. we have much higher photoluminescence quantum yield with a variation on this material, which I'm not going to talk about. So is this emission via quantum cutting? Another way that you can sort of test the hypothesis that it is quantum cutting is the following. So if the mechanism is indeed quantum cutting, the near-infrared photoluminescence quantum yield should decrease abruptly when you decrease the bandgap twice the ytterbium transition, right? Because you won't have enough energy to excite two ytterbium ions. And 1,000 nanometer is about 1.25 electron volts. So if we decrease the bandgap below 2.5 electron volts, we should stop this mechanism. And one way to do that is by substituting some of the bromine with iodine, okay? So this was done in the case of cesium lead chloride and bromide. So in that case, the cesium lead chloride bromide bandgap is greater. So instead of substituting for iodine, they decrease the bandgap by substituting bromine for chlorine. So as you go down the periodic table, you can shift the bandgap. So they didn't have to resort to iodine. They could just add bromine into the chloride and decrease. And look what happened. Just around 2.5, the photoluminescence quantum yield took a dive and went to 0 from something like 200%. This is a kind of a normalized relative intensity, but it's going from something like 200% to nearly 0. So we want to do this with that material. So we're going to decrease the bandgap of ytterbium doped cesium-3 bismuth to bromine 9 by substituting with iodine and see what happens. So the idea is to decrease that conduction bandgap. Let me do that again. So decrease it so that we stop that emission and the photoluminescence quantum yield goes down. So we do the same thing, except now we turn on yet another source. And we put in cesium iodide in addition to cesium bromide. And then I'm going to report the percent iodide as iodide divided by bromine plus iodine, okay? And so we went up from 0 to 34% without disrupting the structure of the material. And X-ray diffraction peaks shift to lower 2 theta angles, and that's consistent with iodine substitution from bromine and increasing the lattice parameters because iodine is a larger ion. And I try to show it by putting a slanted dashed line here. It's a very small shift, but it's detectable. And the trigonal structure is retained. All the peaks are where you would expect. There is some intensity changes in the distribution, and that's because we're changing the texturing a little bit. So there's no sign of phase separation into films that are iodide and bromide, but there is good mixing of bromine and iodine. As we intended, the absorption peak broadens and redshifts. So this is with increasing iodine, going from 0% the peak to 34%. So we're shifting the bandgap, or another way of looking at it is the excitation of the octahedra. The broadening, I think, is due to what are called band edge fluctuations. So it's not entirely random, but there are maybe some distribution of bromine and iodine, so the bandgap sort of fluctuates and it's inhomogeneous and widens it. Now, the absorption onset for the 34% iodine film is less than 2.5 electron volts. So you would expect photoluminescence quantum yield to take a dive in the infrared. So indeed, so this shows the near infrared photoluminescence quantum yield. So the blue one is the one with the 14.5%. As you go 13, by the time you get to 34%, the highest that we could measure was only 1%. So I want to summarize and conclude and give you a chance to ask some questions. I went relatively fast with this material, and I wanted to give you a flavor of giving you just sort of one material that we're working on. We're working on other materials too, and we have one now that is over 80% and doesn't contain lead, and it is the record for that, and we're just writing that paper. So what I showed you is that efficient quantum cutting at realistic photon fluxes is a viable way to improve silicon solar cell efficiencies beyond the Kaiser limit, beyond 40%. And this is the first time in like many, many decades that we realistically have a chance at doing this. These bismuth-based perovskite materials are interesting. They as lead-free host materials for ytterbium doping. And they may exhibit quantum cutting. We resolved some discrepancies in the reported optical absorption and photoluminescence for this material. And one has to be careful because there are lots of things in the liquid that emit and absorb. And we like PVD where such contamination is absent. So one thing is that bismuth bromide octahedra in solution emits and may be misinterpreted. That should be BiBr6 3- in solution emits and may be misinterpreted. Oleic acid, I didn't show you this, but it emits strongly and may be misinterpreted. And moreover, there are impurity phases like the 316 is an impurity phase that looks a lot like, it emits a lot like the BiBr6 octahedra. It also emits at 383 and may be misinterpreted. So one has to do really careful work. So with doped cesium-3 bismuth-2 bromine-9 with ytterbium, we achieved 40.5% near-infrared photoluminescence quantum yield. And we think that the ytterbium is substituting into the bismuth. There is a fast energy transfer from the 329 bends to ytterbium 3+, and it can compete with a very fast non-radiative recombination. And it's only present when the bandgap is 2.5, greater than 2.5 electron volt. And all of that smells like quantum cutting. And so I'm just going to raise the question that could it be quantum cutting? That, however, remains an open question. To show it completely, definitively, is to improve the photoluminescence quantum yield greater than 100% for this material. So shut down all the other competing mechanisms, make a better material, and improve the transfer to the ytterbium. So I am going to stop here and see if you have any questions.
Thank you, Professor Aydil, for the amazing talk. Yeah, it is really wonderful to understand how a layer of a quantum cutting material on a silicon layer cell proves to be a low-cost approach to increasing solar cell efficiency and the Quasar limit, and how the emission mechanism may involve quantum cutting. Yeah. So if anyone have any questions, they may go ahead. Pradeep Kumar has a question that, firstly, he thanks you for the amazing talk, and he asks about your insights on quantum cutting technology using perovskites. So basically, can you give us some information how economical are perovskite cells compared to traditional solar cells and about its lifespan?
Yeah. So thank you for the kind words, first of all. And I want to make one thing clear. What I'm working on is not a perovskite solar cell. So people who work on perovskite solar cells use the perovskite as both as an absorber and as a material that creates the electron-hole pair, and then you extract the current. That is not what I am doing. It's a very, very crowded field, and that's not what my group does. And there are many, many fine papers who have done the economic analysis, and they argue that the way that they make the perovskites and the efficiency improvements, because you can utilize liquid synthesis, etc., brings down the cost. So they will argue that it's low cost, or it will be low cost compared to some other methods. We can debate separately whether one buys that argument or not. I personally do not. I think silicon solar cells will dominate in the foreseeable future. First of all, there are some startup perovskite companies, but the stability is an issue. There are lots of questions about perovskite solar cells. It is a hot area, but when it comes down to commercialization, there are lots of things that you have to do. Okay, so to put in perspective what I am doing, I am trying to make a stable material that only goes on a silicon solar cell. So I am using the perovskite to enhance the existing silicon solar cell technology. So, you know, you can imagine that this could be in lieu of an anti-reflective coating. Okay, in fact, it has anti-reflective properties, but it does more than what an anti-reflection layer does. It takes and shifts the spectrum to a beneficial region. Okay, so it is no more different than the existing technology, and all we have to do is make it efficient in terms of conversion and make it stable over time. And I saw a question on the stability of the material. So these materials are stable in air. We take it out and then we look at them over a period of weeks and months. This one is stable, but it does decay. The new one that I did not talk about is even more stable. And that's without any encapsulation, anything. It's just sort of sitting in air, you know, without any precautions. It is rock steady if you keep it in glove box. I didn't show you that data. What we're trying to do is optimize the material first and then take reliable long-term stability data. But just sort of our curiosity, keeping track of a few films over a month period, they look very, very promising.
Okay, thank you, Prof. Aydil. Does anyone have any other questions? Okay, so someone asked, about your perspective on what about oxide perovskite solar cells?
That is a good question. The issue with oxide perovskites is that their band gaps tend to be wider. And if you look at the Shockley-Quessier, you know, it has to peak around, you know, 1 electron volt or so. Whereas oxide perovskites tend to be wider band gap. So it doesn't quite match the solar spectrum. There's also chalcogenide-based perovskites, you know, sulfur, and those have lower band gaps. And I have colleagues who are working on these. There are people working on these. They are difficult to make, but it's an area. It's a nice area, I think.
Thank you, Prof. Aydil, once again. Does anyone have any other questions? Okay, yeah, so I think we do not have any more questions. The conclusion of the session now. Yeah, thank you, Prof. Aydil, once again for the exciting talk. And also thanks for accepting our invitation and lending us your valuable time to deliver this talk. Yeah.
My pleasure. Thank you for having me.
Yeah, thank you very much.
Bye-bye.
Bye-bye.